Welcome back after the first break. I hope you emptied your brain a little bit and then we can continue. We will have a short summary about the pore sizes and then we'll have a little background about tortuosity and I will show you how to calculate this on Geodict. For the summary of the pore size distribution, I want to re-show you the slide where the granulometry and the porosimetry experiment is compared. The image on the left shows the pore volume with the diameters colored gradually. The wet pore volume describes the pore volume with diameters around 40 micrometers or larger. The green ones shows diameters around 20 micrometers and diameters smaller than those 20 are colored normally in blue, like here. As shown in the illustration, the pores found by granulometry can be isolated in the structure and there can be no connectivity or accessibility to the faces of the structure. So this value cannot be found via a physical experiment. For the porosimetry, this is different. When measured the porosity in the laboratory, for example the mercury intrusion porosimetry or the liquid extrusion porosimetry, the isolated pores are not measured as large pores because they lay hidden to the outside world behind small bottlenecks and they are therefore only measured as having the diameter of the bottleneck by the measurement devices. Consequently, the computed pore size distribution by porosimetry takes the connectivity of the pores into account. On this slide, I want to re-show you the Geodict result file for the pore size distribution to compare the results. And you can see that on the granulometry experiment that there are a lot of pores with big diameters that have no connectivity to the outside world and that the bottleneck is about 4 micrometer for the porosimetry. And then the larger pores are not in the experiment. After analyzing the pore size distribution, we now concentrate on the tortuosity that indicates the length of the necessary detours in the microstructure. Normally, the direct ray is blocked by grains of fibers, for example, so the ion need to search for another path. So that would be the direct path, and that's the detour that the ion has to take to find another way. And the tortuosity is calculating this ratio. To do this, we go on predict and we choose the first module, diffpredict. We choose it. We see that the module is loaded inside there. And here the bulk Laplace diffusion for very, very small Knudsen numbers are already in. If it's not in, you just click here and you choose the second one. And then you click on solver options. And then you see the window that's opening. The constituent materials will not be changed, but you can check that there's no mistake going inside. Then you go on boundary conditions and you check that the computation direction is on X and Z direction. You can go to you look on boundary conditions for the diffusion direction. It should be on symmetric Dirichlet condition. And then that's the next thing is the solver. Which solver are you going to take? And for this example, we are going to take the Lear solvers. If you have doubts which one to take, you can read the tooltip that explains you which solver is good for which application. For us, the Lear is the right one. We looked at it as a check mark at write diffusion flux into the solution file. And when everything is done, we click on OK. And then we click on Run and wait until it's done. If it's the second time you do it, you can, for me, I already did it. You can here overwrite the results, and it will need some seconds. The window was opening is because I already did this before for some testing, and I already have the file. And that's something quite good to know for Geodict. If you do a simulation a second time and the first time and you can either rename it, you can overwrite it, or you can click on backup, and then is Geodict automatically making a backup folder where all the old simulations are going to be inside. Now we have to wait a little bit because the simulation needs maybe something about 1 minute. So you can just relax a little bit and wait. This slide was taken from the Geodict user meeting in 2019. The corresponding talk was given by Lorenz Holzer from the ZHAV in Zurich. It shows that there are a lot of different definitions of tortuosity, and similar as for the pore sizes, these different definitions may lead to very different results. The geometric ones measure the length of the path that a particle would have to take. Like, for example, calculating percolation path, which are the widest through path, and comparing their length to the thickness of the sample. The physical-based measurements calculate the flow or diffusion through the sample and calculate backwards the tortuosity. Definitions on this type of calculating tortuosities can be found in literature, and the tortuosity resulting from the physical methods are usually higher than those that are calculated from the geometric methods. In Geodict, we have the tortuosity app that calculated many sorts of tortuosity that are shown in the slide. Nevertheless, in this workshop, we are going to concentrate on very common definition where the tortuosity is based on diffusion through the sample. And this definition was defined by Norman Epstein, and the corresponding citation is in Geodict. And here the modules are labeled. This is why we'll have a view on diffusion. Diffusion refers to the movement of fluid molecules in porous solids, and the method to choose to calculate it depends on the likeliness of the ions to collide either with the pore walls or with other ions. So here the pore walls, and here are other ions. The Knudsen number is defined as the ratio of the mean free path length to representative physical length scale. The Knudsen number is shortened with Kn. The Knudsen diffusion occurs when the pore diameter is comparable or smaller than the mean free path length of the molecule diffusing through the pore. Under this condition, the collision with the pore walls becomes gradually more likely and the diffusivity is lower. And both methods that mean the Knudsen and the bulk diffusion are approximations for different cases. And in our case, the bulk diffusion is the method to choose. So for small Knudsen numbers, and here is Darcy's law that defines the diffusion. Because it was needing a lot of time, I did a little cut here until the result viewer was opening. Here you can look at the results, the report. You can see the relative diffusivity in X and in Z direction. You can see the tortuosity factors in X and Z direction, the kappa tortuosity factor and the tau. Here's also the citation of the paper where the formulas are from. You can check the concentration, that is a linear plot. You can see that the diffusion flux in the direction, the upper and the lower standard deviation, and also the convergence for the simulation process. If you get on data visualization, we can look at both, but in this workshop we are just looking to the x direction. To the volume field, we load it. We have this window opening, and we wait a second. And now I see the volume field and the structure together. If I unclip this, the structure, I can see here the volume field. And if I make the diffusion flux higher, like this, I can see where the fast diffusion is, and I would say it's just always inside the pore. And if I now unclip the volume field and go back to the structure, I can now show you how to make a nice picture and a nice visualization. You invert the structure, you start with the Z, and you see this clipping, and you go to the Y, and now you have a part of the volume filled with the structure, and a part is still empty. Now you can make a check mark to the streamlines, and now the streamlines are visualized everywhere, but the structure is not everywhere, so you can see where's the structure and where are the streamlines. And you can also animate the streamlines to have the streamlets. Click on play, and then you see them in a nice animation. We can also make a video from. After enjoying this nice visualization, we go back, we make the streamlines out, we go to the structure, we make the clipping back, and the invert. So we have the structure back, and now we start our preparation for the charged half cell simulation. For this, we first have to permute the structure and to crop it, and then I will continue to explaining anything. To permute the structure, you go on model, you go on process geo. Here is already permute inside. If it's not, you have to choose this one. Then you click on options on edit. You check that here is rotate, Y direction and clockwise. You click OK and click on permute. That's going to permute the structure. You can do it the way I showed you, or you can take a shortcut. You go on structure with a right click, and here you can also go on permute rotate, and the same window will open. We go back to the process geo, and we click here on process and then on crop. That's in the second pull-down menu. Or we can also take the shortcut, make right click to structure, here process, and then crop. It's the same window that's coming out, and I already made the numbers inside that you will need. It's for the X, it's 75 and 75, and for X and Z Y and Z direction, it's 225. You also crop the volume field. Or you don't need it, in fact, and then you click on run. You wait a second, and then you get this structure that is not so representative, but the simulation will be much faster on it. Now we move to battery dict. It's here. We see here that the module changed, and we click on predict, charge half cell, and then we click on edit, and then we see that there are some windows opening, and it's so you can see the materials that are inside, and you can see the role that they are going to play in the battery. The anode will be a lithium reservoir that is not limiting the performance of the cathode material. We see here a lithium reservoir. You can click on Edit Model. Then you see here the Butler-Volmer rate constant is 0.4. Click on OK. And then you click on Anode Current Collector. You click here. You see that it's a manual current collector material with an effective electronic conductivity of 1000. If it's not this number, you put this number inside, you click on OK. And for the next thing, you go to the electrochemistry. You can here view the material for the electrolyte. You can see the ionic diffusion constant and the transference number. And you can also see this for the binder material and for the electrolyte. Those are the electrochemistry properties. Same as for the electrical conductivity, where you can see the numbers that are used in the experiment. Now we are going to define the battery charging experiment a little bit more in detail. For this, we go to Experiment, and we are going to set a charging profile. Here we can charge, we can discharge, or we can set a charging profile. And we will select the first point, charge battery cell. And we can change here the charge rate. We'll let it on 1. That means that it's in 1 hour the cell is going to be fully charged. We go and select the start and end condition, initial and final electrode SOC. Here we can set that we want to charge from 30 to 80%. We can also charge from 5 to 95%, so it depends on the experiment you want to do. The boundary condition stays on symmetric, and the computational direction is going on X. The next window here is the solver. We'll select the Lear solver that is much faster than the Best Micro. We have the parallelization, so my computer has maximum 8 cores, so I will calculate on all of them. And here we also have the error condition, so when does the experiment is going to stop. On the output option, we can select that if you want to calculate the estimation only, we can make a check mark here, but for this one we don't really need it. And in the last window you can see the formulas that are going to be solved in this experiment. I think it's time to click on OK, and then to click on Charge. And the simulation will need something about 8 minutes, and that's why we will have a break now of about 10 minutes. And if there are questions, just ask them, otherwise we'll see you later.